Any questions that you might have before we get started?
I had a question.
Yeah, sure.
So on the video that was for the pre-class quiz, the number 3 where it was translating from English. So there is no smallest real number, and it was for every real number x or for any real number x, there exists a real number y with y being less than or equal to x.
Mm-hmm.
I was wondering, why is it y is less than or equal to x and not just less than x? Because if you say or equal to x, doesn't that imply that at some point there is a smallest real number?
So if there was another number which was equal to x, then that would imply x is not the single smallest number, but there are two numbers that are the smallest.
I don't think I follow.
So it's possible that you could have in some universe two numbers that are not the same, but are both the smallest possible number. So this is just ruling out that possibility.
Oh, okay. I see.
Yeah, so if there were another number that were equal to x, then x would no longer be the smallest because there would be another number that was equally as small.
Okay, I gotcha.
Yeah, that's a very subtle point there. Yeah, but that's a good question.
Thank you.
Anything else? Okay, so I want to just quickly share our page, Canvas, to make sure you're aware that I put up all the materials for almost all of the materials for week 2 over the weekend. So you should have plenty to keep you busy once you wrap up the homework that's due this evening. Today, it might be helpful to download them. We're going to be working with these two worksheets over here. So worksheet 3 and worksheet 4. Worksheet 4 we'll start today and we'll finish it up on Wednesday. So we'll spread that out over a couple of classes. So thanks for the quizzes today. You've got another short quiz due before Wednesday's class, and homework assignment number 2. I haven't posted the PDF file. I will get that up this afternoon. So once you wrap up the homework due tonight, you can get started on that. Any questions about the work? Okay, so let's take a look at some of the stuff that you worked on for the reading quiz. So you asked some questions about that. Happy to answer any others. That was my plan. So for the reading quiz, it was getting used to some of the notation that you may or may not have seen before. So these quantifiers for all there exists, and that in symbol, as well as different notation that we use for number systems. I would love to ask these sorts of questions on the Canvas quiz. I'm just a little bit limited in the question type. So the main point here is not just to know what these symbols are, but to be able to translate these things between symbolic logic and English. Oftentimes, a problem is going to be stated in English, and we're going to want to translate it symbolically to kind of see the structure in the statement that we're trying to prove. So there was a question, I don't think about any of these, but I went through these in the video. Any questions about these interpretations?
I have a question on B and C.
Yeah.
If the first two parts, like they're just flipped, why does that, like the sentences don't look the same?
Yeah, so when we flip these two things around, so over here, we started with this, and then we said there exists, right? And then we flip them around. And so when you change the order of things, that oftentimes changes the meaning of the statement, which is what happens here. So the first one is saying for every number x, for all x, right, there exists a number y for which y cubed is equal to x. And that's a true statement because given any number y, or given any value for x, right? I can find such a y by just taking the cube root of x. And then cubing that would give me x back. So this statement is true over here. When we flip them around, that changes the meaning of this statement. And this is actually false because this is saying that there exists one number y with the property that when I cube y, I get every possible value of x, right? And so that one doesn't make sense. So this one is false.
Okay, that makes sense. Thank you.
Yeah, and so it's almost like learning a new language in some sense with all of these symbols. And just like, you know, when you change the order of a sentence around, sometimes that doesn't change the meaning, it's stylistic, and sometimes it does, yeah. Any others about these? And then we went the other way and practiced going this way. So yeah, these were done on the video, but I want to give you a chance to ask in person if you had any questions about them. And I think what's important with these statements A, B, and C, well, at least A and B, I should say. A and B are conditional statements. If this is true, then that is true. And so we do put the universal quantifier in front of that because we're really thinking about does this conditional statement hold for all such values? But any questions about these? Yeah.
Confused by C.
Okay.
I know that you explained it in the video, but I guess I don't understand the last part where you're saying y is smaller than or equal to x.
Yeah, so this is saying there is no smallest number. So let's say I think that x equals minus 27 is the smallest number, right? So, okay, if I find a y that's smaller than it, clearly that is not the smallest number. I think maybe the question is, well, why is there an equal sign over here?
Yeah.
And yeah, so I think this is what Stephanie was asking about, and it's a very subtle thing, but if we assume that it's possible that there could be two smallest numbers, so clearly that's not the case, but we could have some other y over here, which is equal to minus 27, but a different number from 27 if there were some weird mathematical universe. And then that would tell me that minus 27 is not the smallest number, but there's another number that's equally as small as it.
Okay.
Yeah, so if the issue is this or that, I'm not too concerned by that subtlety, yeah. If you kind of go on this assumption that if two numbers are equal to each other, that they have to be the same number, then yes. What I said over here is what we're really saying is there's another y that's not the same as x, which is less than it, and that's fine to say too. Yeah.
Thank you.
Okay. So let's. So were there any other questions? Sorry, before I turn pages. Okay, so let's think about a sentence like this. So here's a conditional statement, and if you downloaded this, you can kind of just ignore what's hidden behind the box over here. We'll reveal that in a second. But if x is an integer, then x is a multiple of 6. So there's a statement meaning it's either true or it's false. So I'm just kind of curious to take a poll and see whether you think that statement is true or false. Okay. If you haven't gotten your answer in, take another 10 seconds, please. All right, so here are the results from the class. So we had 14 falses and 1 true statement. So let's take a look at what is going on behind here. So on the one hand, you might think that this, okay, so I guess the question is, like, there should have been another option, which is this even a statement? Which is what I meant to ask, right? And so the question is this thing definitely true or is this thing definitely false? And there are two ways that you might want to think about this. You could say it depends on x. If that x is 6 or 12 or 18, there are some even numbers that are divisible by 6 and other numbers that aren't. So this is an open sentence. Or you might be thinking about this as saying, this has to be true for all values of x. And so I just want to say that there is some ambiguity here with how you may interpret that. And that's bad. We're doing logic here, and there shouldn't be any ambiguity. So it's understood in mathematics that we assume this is a universal quantifier. So that means that we're making this statement about all such values of x so that we can then logically say that this thing is true or false. So in this sense, mathematically, we would consider this a statement, and we would consider this statement false since it's not true for all values of x. X equals 4, that is a violation. So yes, so when we state these things, what we really mean here is for all even integers x, if x is even, then x is divisible by 6, which is the same thing as saying a multiple of 6. So we really are talking about all such values. Okay, questions? And you're welcome to chat them in as well if you have any questions. I got that open. Your questions will come only to me. Okay. Let's start by taking these for all statements and try and write them as conditional statements. That is mainly what we're going to be proving in this class. If some stuff is true, can we then show that some other stuff is going to be true? So if I've got a statement like this, I would like to write it as an implication. If something, then something else. And this is going to be like the first step when we're going through our proving statements on the next worksheet. So on the one hand, we can read this very literally saying for all x, should say for all real numbers x, right? We've seen this already. There exists a real number y, so any ideas how we can change this into a conditional statement? We need a statement and a statement over here. Anybody have an idea about what could be in place of P, what can be in place of Q?
Can you say P is if there is real number x, and then Q is then there is real number y, so that y to the third is equal to x?
That would work. Yep. So we could say, okay, if x is real, then there exists a y such that cubing y gives me x. And again, that value of y is the cube root of y. So we could prove that statement, but you would want to start by saying, if x is real, we're going to start there and then kind of move towards trying to prove the conclusion. If we did not assume that x is real, like if we said given any integer x, there exists another integer y, then we might run into some problems. But this is true for real numbers. Okay, and any questions? So our kind of P statement here is x is real. And then all of this stuff over here, that's our statement Q. And now we've got this in the form P implies Q. Okay, thank you. Somebody else want to take a shot at B? What would be the hypothesis and what would be the conclusion in that statement? All right, I'm gonna just randomly go in my, all right, Dylan, are you with us? Hey.
Hi.
Yeah, so what might go first here? So the idea is we've got statement B and I want to write it as a conditional like we did with A. So what's the assumption here? So Dylan, what would be the assumption here? What's the hypothesis?
That x is even.
Yeah, so we got x is even, right? We kind of see that over here. And then the hypothesis would be over here. So what I'd like to do is write this as an English sentence, right? So here we're starting to kind of move away from the symbolic notation. So rather than use this little implication, we could say, for example, if x is even, then either x is 2 or x is composite. Okay, and so a composite means that it can be written as a product of two numbers that are less than it. Okay, this is a true statement here, but it's useful to write it out like this before we try and prove it. We'd like to know what information am I given in this problem and what information am I trying to prove. Any question? Okay, so in C, every differentiable function is continuous. Somebody want to take a shot at what the hypothesis would be here?
If x is continuous?
Hmm? You want to finish that up, John?
Then f of x is differentiable?
Yeah, I think what we want to have here is what do you guys think? You guys agree or disagree?
I think it would be backwards, right? Or
So you think
three.
the given or the first statement is differentiable?
Yeah, I've kind of had that same issue on all of these problems. Like, it seems like you could do it either way.
Okay, yes. So Here we've got it set up both ways. One of these is correct, one of them is not. So they're not saying the same thing. So this one is saying if f is differentiable, then f is continuous. So we would read the red one as saying and the blue one we would say is saying if f is continuous, then f is differentiable. So these are both statements. They're not the same statement. One of them is true, one of them is false. So I'm not asking which is true and which is false, but which one matches up with what we were given over here.
I think it's the red one.
Why is that?
Because in the sentence it says every differential function is continuous. So if you're given a differential function, then you know it's going to be continuous, but it's not necessarily the other way around. So like not for every function that's continuous is not always going to be differentiable.
That's right. What's a counter example for that?
You mean?
What's a function which is continuous but not differentiable?
Wasn't that the fractal thing we looked at?
So that was actually an example of a function which is everywhere continuous but nowhere differentiable,
Yeah.
which is kind of a weird, but yeah, that would work. That's right. So that would be a counter example. I think an easier one might be something like this, right? That's continuous, but it has a corner, so it's not differentiable. So that is not a true statement over here. And the second statement, this actually is a true statement over here. It's true that if something is smooth, then it has to be continuous. But this statement, what most important, statement C is definitely saying we start with a differentiable function and then we're claiming that it therefore has to be continuous. So that's why we start with f is differentiable and then we end with f being continuous. So if we wanted to state this clearly, say in English, this is equivalent to saying if f is differentiable, then f is continuous. And again, that is a true statement. Yeah, so really important, to get these translations down before we get too far into proving things. Because the first thing is we want to be sure that we're interpreting the statement that we're trying to prove properly. Okay, and so the last thing I just want to talk about is how we can negate statements that have quantifiers in them. So one way that we could state this, if we wanted to state it, say, symbolically, so we can't really state some of these things with mathematics, but here this is saying, right, for all students, it should be the case that X is a math major. So how could we negate this statement? What would cause this? Remember, one way that we can think about a negation is it's what would cause this statement to be wrong.
Well, if there's just one student that's not a math major, then it's wrong.
That's right. So we don't need a whole lot of students that aren't math majors to prove this. We just need one. So kind of the important thing here is that when we negate a statement that has a universal quantifier for all statement, its negation is always going to have the existential quantifier, the there exists. So here we're going to say that there exists a student in this class. And what Do you mind saying that again, Brandon? And what should be true about the existence of this one student?
They are not a math major.
That's right. Thank you. Okay, so here what we've done is we changed the universal quantifier to an existential quantifier. And then we also negated the last part of this sentence, right? So we changed that to an existential one, and then over here, we just negated the original statement. And this would be exactly saying that there is a student in this class who is not a math major. There are several of you. Okay, so for example, based on what I know about this class, the original statement is false. Everybody is not a math major. The negation is true. Statement number 2 is saying there exists a student in this class whose first name starts with K. How would that statement be false? What would make that statement false?
There are no students in the class whose first name starts with a K.
Okay, that is correct. But we don't have a quantifier for there are no. So let me try and restate this in a way that we can use quantifiers in this statement. So another way that I could restate this would be, not like that, sorry. I could say, okay, for all students in the class, what should be true about all of those students?
None of them have a first name that starts with K.
Oh, it's a first name. Yes, thank you. First name. Right, for all students in the class, right, they all don't have a first name that begins with K. So the kind of analogy I want to make here is that when we negate a statement that has an existential quantifier, we convert that into a universal quantifier, and we still negate the original statement. So we change do have a name to don't have a name that begins with K. Okay, so for example, something like this, everybody loves Raymond, for example. This we could say is that there exists one person who does not love Raymond. I am not a huge fan of Everybody Loves Raymond. You guys might not even know what that show is anymore. It sounds so long ago, but someone in the math department is apparently. So why don't you give this one a try over here? This is a little bit more mathy, but we've seen this one before. What I'd like you to do is negate that statement.
since it's an if-then statement, does that mean the negation is also an if-then statement?
So remember that when we negate an if-then statement is when we negate it, it turns into the hypothesis is true and the conclusion is false. So when you negate a conditional statement, you might be able to state it in English in different ways, but technically what you get is a conjunction statement. You need two things to be true, the hypothesis to be true, but the conclusion to be false as well.
So for this one, we can say that the first state that P is true, where X belongs to a real number, but Q is not true, where Y does not belong to a real number, or?
Yeah, so we can state this as if X is real, then there exists Y such that Y cubed is equal to X. Okay, but so there are different ways that we might want to think about this, but again, like when we want to negate something, what we're doing is we're just saying what would make that original statement false. So let's think about it. We do have some ways of trying to do this systematically. So what am I going to do with that for all X?
X does not belong to a real number, or X is not real?
So remember up here, when we negated a universal quantifier, a statement that had a universal quantifier, it turned into an existential quantifier. And when we negated a statement that began with an existential quantifier, we wound up with something equivalent to a statement that involved a universal quantifier. So if this statement begins with a for all X, we're going to try and negate this. What should we change that universal quantifier to?
There exists a real number X.
That's right. And so really what this is saying is if you want to negate this statement, all we need to do is find one X that doesn't hold for the original statement. So we would say that there exists an X. Okay, and now let's think about what would go wrong with the rest of this statement. So there's gonna exist one X and someone just texted in such that there is no Y with Y cubed equal to X. I think that should work. And so that would negate the original statement. We just need to find one such X that doesn't have a corresponding Y value for that to hold. So in some sense, when we negated this conditional statement, though we haven't stated it in that plain terms, we are dealing with a conjunction. We need two things to be true. There is no Y and Y cubed is not equal to X. So I think the big takeaway here is that when we negate these quantifiers, we get the other quantifier back in the negation. Okay, any other questions about these quantifiers?
Yeah, I have a quick question.
Sure.
Would it be okay, like, to say like there exists an, so instead of saying there exists an X such that there is no Y for which Y cubed equals 3, could you go ahead and say that for all X there exists at least one X that does not equal Y cubed?
Say that again. For all X.
So for all x, there exists at least one x that does not equal y cubed.
So I think you just don't need that initial thing, right? You said for all x, there exists an x. So you haven't changed the logical meaning of that sentence if you just chop off that for all x. Really, the most important thing is that there exists one x. Yeah.
Okay.
So there's nothing wrong about saying for all x, there exists an x. It's just not necessary to include that.
Okay.
Yeah. Okay, so if there aren't others, let's start to get into proving things. That's what we're here to do. So we definitely want to get some of these ideas of logic down before we jump into proofs. In Chapter 4, they introduce you to our kind of first proof technique, which is going to be a direct proof, and we're going to use direct proofs to prove conditional statements and some biconditional statements. So just some terminology that I want to be sure that we're clear about, since we've got all of these different terms in mathematics. We have an axiom, definitions, theorems, proofs, lemmas, corollaries, all these other things as well. So an axiom is something that is like so clearly evidently true that we have to start somewhere. We have to start with some truth, and these are the things that are self-evident. So for example, I just put some examples of each of these. The commutative axiom says that, okay, when we add numbers, it doesn't matter whether I take x plus y or y plus x. There's really nothing I can do to prove that other than say, trust me, that seems pretty evidently clear. So we have to start with some beliefs, and that would be our axioms. And in mathematics, we try and start with the smallest number of axioms possible in order to prove all true statements that can be true and to prove all statements that are false. But there is no such set of axioms, unfortunately. Okay, and then a definition is just, explicitly stating the meaning of a mathematical idea. And then we have theorems, which are statements that are not self-evidently true that require some convincing. So intermediate value theorem would be an example of a theorem, right? It's not totally clear why that statement is true, and there's some argument that needs to be made to support that statement. But this is true. And then we can think about different proofs that we can do and which are most convincing. So our goal today is going to be using some definitions. We're going to try and prove some theorems using a method called direct proof. So direct proof is probably the most preferred way to try and prove things in mathematics. So we'll learn some other techniques, induction, contradiction, and so on. I'll just say out of these methods, it's not just can you prove this, but oftentimes it's who has the best proof. And I think a direct proof usually sits on top of the pyramid of like, these are the best proofs. So that's why we'll talk about this one first. And we actually have some steps that we can keep in mind when we're trying to prove these things. So it's going to start with an if-then statement, and it might not always be clear that what is P and what is Q. So I think a good first step is to do what we were working on the previous worksheet, which is let's carefully identify what the hypothesis and what the conclusion are. And then we think about how can we prove this? Well, let's assume that P is true, and then we're going to try and show a bunch of logical connections to try and get our way down to the conclusion and show that therefore the conclusion also has to be true. So we can start one together. I'll do one, and then I'm going to have us break up into breakout rooms and think about some of these other statements, and we'll wrap up whichever ones we don't cover today on Wednesday. So, all right, here's our first proof for this semester. So here's the statement. Let x and y be integers. If x is even, then x times y is even. And in case you missed it up here, we've got some definitions. This one is clearly not right. That one should be odd. So if an integer is odd, then it can be written as 2a plus 1 for some integer a. And even was on the previous page. So I want to try and prove this statement. The first thing I'm going to do is say, okay, what are my statements P and Q? And in this example, that's fairly clear because this sentence is already if then. But that might not always be the case. So what we're going to assume is that x is an even integer. And then what we're going to try and prove is that x times y is an even integer. And one thing that's really nice about mathematics is we deal in fact in mathematics. And we don't have fake news or any of those sorts of things when we're trying to prove things. So there's going to be no subjectivity to how we're grading things. You know, if your logic is sound and true, then you'll get your marks. If it's not, then you'll lose some points. So it should be really clear what a good answer is, what an unacceptable answer is, just making sure that you can connect these logical statements. So we shouldn't really assume anything at face value, okay? If you should assume that your audience is not me when you're writing these proofs, but you should assume that your audience is like somebody else in the class, that you really need to try and convince them what you're saying is true. So first we identify P and Q, and then we start with the assumption that P is true. So in this case, we're going to assume that x is even. And then we go to the definition to say, well, what exactly does that mean? Well, here's what that would mean. So let me write that out mathematically. So let's assume x is even. So this means that there is an integer a such that x is equal to 2 times a. So that's our starting point in this proof. And as I'm stating things, let's be really careful to write incomplete sentences as well. Okay, and so then what we definitely don't want to do is assume the thing that we're proving, right? So we don't know that x, y is odd. That's what we're trying to show. So let's try and move in that direction. So I could say, okay, well then, therefore, this product, x times y, how could I express that in a way that's going to lead me to show that x times y is even?
Write it as 2a times y.
Exactly. So this was our assumption, right? We assumed that x was even. So I know that x can be written as 2 times an integer. So let's use that given information, plug it into this product. And now we've shown that x times y can be written as 2 times a y. So does this prove that x times y is even?
Yes, because it's 2 times an integer if you assume that AY is an integer.
Well, that's right. And careful, we don't want to assume A times Y is an integer. That's right. So there is a subtle thing that we just need to be sure that we convince the reader of this proof, and that is a number is odd if it can be written as 2 times an integer. So we just want to be sure that we are convinced that A times Y is an integer. And so here we could say, since A is an integer, and we were also told that Y is an integer, then A times Y is an integer. Okay, and thus now we have shown that X times Y is even because I've shown that it can be written as 2 times an integer. And then when we're done, typically we put a little box at the end to show that that is the conclusion of our proof. So we use these boxes in mathematics at the end to just tell the reader, bam, I'm done. You're welcome. Use a smiley face or a check mark or anything else, but it's good to use something to let the person know, like, okay, that proof is done.
I have a question.
Yeah.
So we don't necessarily have to prove things like X equals 2A. We can make, we can take like other proven statements to prove our statements. Is that right?
We are allowed to say that X is equal to 2A because that's our assumption. So we start by assuming statement P is true. So statement P was X is even. And so we're allowed to use the definition of even. So that's usually like the next step is you say, okay, I'm going to assume that P is true. What does that mean? What does it mean that X is even? Well, by definition, that means I can write it as 2 times some integer.
Okay, thanks.
So I think what is really common to hear when dealing with proofs or math problems in general, but particularly proofs, is like, I'm having a hard time knowing what is the first step that I should do. And that can be tricky. And so, and it's going to be different depending on the statement that you're trying to prove. But if you're doing direct proof and you're totally stumped about where to begin, I think a very good first step is just to identify what is the statement P and what is the statement Q. And that's going to tell me here's where I start and here's where I want to end. You're going to start with P and hopefully you get to the end and you show that that would have to imply that Q is true. Okay, any questions about the sketch of the proof that I just did here?
I actually have another question about proofs in general.
Sure.
So if somebody came along and they could prove that your assumption that P is true is wrong, everything kind of falls apart. So all you're doing is just being able to, prove it, assuming P is true, but we don't have to prove that P is true.
Yes, we don't have to prove that P is true. We are allowed to assume that the statement P is true. So you're going to have some conditional P and Q. P and Q are statements themselves. They have to be either true or false. And so you are going to start by assuming P is true.
Okay.
So X is a number and we are assuming that X is even. And if someone tells you, well, what if X is odd? Then you can tell them that has nothing to do with this proof. We are trying to prove that if a number is even, that's going to have to imply that x times y is also even.
Is that kind of like our vegetable example where we're saying like, well, assume you ate your vegetables. No. We're not talking about if you didn't eat them.
So yeah, we're trying to prove here that the total statement up here, this conditional statement, that's right, follows. And so there are different ways that we can do this because there are different ways that conditional statements could be true. You're right. So we could have a false, and that might lead to a true. So I'll just say there are other proof techniques for these conditional statements that might involve assuming something is false and vice versa that are valid. The method that we're going to first talk about is, in particular, one way that we can do this is looking at the first row of that truth table, which says if P is true, then the only way that statement is going to be true is if the implication is also true. But there are other things that you could consider, and we'll kind of just group those into like, that's going to correspond to a different method of proof. Okay, so let's give some of these a shot. So let's see how far we can do. And again, I'm not expecting us to prove, 8 things in the rest of the time. So take your time, but I want you all to think about it, since it's one thing to listen to somebody do a proof and say like, yeah, that makes sense, good proof. It's totally different to have to write these yourself, obviously. So I want to give you a chance to do that and give you a chance to talk with your classmates about it, and then we'll compare notes. So let's start. I'm going to shoot you into the breakout rooms, and let's start by thinking about number 2. So let's kind of summarize what happened in 2, and some groups were moving on, and I think some of the other proofs probably have a similar feel to it if you had a chance to move on and think about 3 or 4. So question 2 was saying if x is an even integer, no, what was 2 saying? It was odd, right?
It was an odd integer.
Yeah, sorry. So we're going to assume x is odd. That's right. We did the even one. Then x squared is odd. Okay. So we've got statement P, x is even, or sorry, x is odd, and statement Q is x squared is odd. So again, here's a good first step. And then what the proof is ultimately going to look like is we're going to assume P is true, do some stuff, and then in the end, we're going to say, okay, well, therefore now we can see that Q definitely has to be true. And so, yeah, this is the most important part, is that squiggly stuff in between. And that's we're going to need to do different things depending on the situation. So let me just kind of summarize this since we're just about out of time. So saying that P is true, in other words, is we're going to say, let's assume that x is odd. And so that means we can write x as 2a plus 1 for some integer a. So that's kind of this step over here. We just replaced P with what that expression was. And now we can say, well, x squared, what is that going to look like? Well, that would look like 2a plus 1 squared. And so some people were asking, like, how can we write out, what's the proper way to write equations in a proof? Well, you just can write an equation, right? An equation is a sentence. So here we've got 4a squared plus 4a plus 1. So from this, we can see x squared is equal to 2 times 2a squared plus 2a plus 1. Okay, factoring a 2 out of each of the first two terms. So what we've just shown is that x squared now can be written as 2 times an integer plus 1. So since we've shown that x squared can be written as 2 times an integer plus 1, by definition, x squared is odd. And there we go. That would be it. So I like to think of these things as like some sort of game. Like we've got some rules, some assumptions that we can start with. How can we prove the conclusion? There are other ways we can prove these things, but again, I think this is the most elegant way of doing things, is proving them directly. Okay, so sorry, we're out of time. We're over time by a minute. Sorry about that. If you have any questions, you're welcome to hang around after class. I can stick around for a few minutes. Otherwise, give the homework uploaded by midnight tonight, and I'll see everybody on Wednesday. Thanks.